If you take a heavy excavator and, accidentally dig into a buried high voltage line, you aren't just looking at a neighborhood blackout. I mean, you are looking at millions of dollars in project damages, crippling delays, and a potentially lethal explosion.
Yeah, absolutely. It's a massive risk.
Right. Yet every single time you walk down a city street or wait for a bus or to stroll through your neighborhood, you are stepping directly over a completely invisible, highly volatile, and just wildly tangled web of critical infrastructure.
Completely. It's all right there under the pavement.
We are talking pressurized gas mains, those lethal high-voltage power lines, and the delicate hyperscale data center fiber optics that literally carry modern society's information. It is a subterranean maze, and navigating it requires a level of precision most people never even think about.
It really is an incredibly high-stakes environment. I mean, you have civil construction firms running these massive earth-moving operations, and the only thing standing between, like, a routine Tuesday and a catastrophic utility strike is a highly specialized set of rules and, well, some incredibly advanced mapping technology.
The margin for error is what, basically zero?
Essentially zero, yeah. Especially when you're dealing with legacy infrastructure mixed with brand new installations. It's chaotic down there.
Which is why, for this deep dive, our mission is to explore exactly how professionals map out this invisible underground world before anyone is legally allowed to put a single shovel into the dirt.
Exactly.
And to understand how they do this, we are pulling directly from the Before You Dig Australia, or BYDA, guidelines on the Australian Standard 5488. And to look at the technology making it possible, we're examining technical literature and a really fascinating breakdown from TMG regarding radio detection's MRX precision cable locators.
Yeah, the pairing of those sources gives us a really complete picture. Because, you cannot fully appreciate the engineering behind this technology without first understanding the incredibly rigid legal and safety framework. That framework dictates exactly when, where, and how you are allowed to break ground.
Right, because you can't just guess.
Exactly.
Yeah.
Australia has built a very robust standard for this, and the equipment has evolved specifically to solve the physical limitations of that framework.
Okay, so let's unpack this, because if you are a civil contractor, you don't just walk out to a site and start digging based on a hunch. The Australian Standard 5488 is, well, it's essentially the alphabet of safety for subsurface utility engineering.
That's a good way to put it.
It dictates the required quality of an asset location, breaking it down into 4 distinct quality levels, starting at D and going up to A. Let's start at the absolute baseline, which is quality level D.
Right. So quality level D, or QLD, is the foundational first step. This is the information you pull directly from the BYDA records or like municipal maps.
So just paperwork.
Just paperwork. You look at these documents, and they give you a general indication of what assets are likely to be sitting inside your designated danger zone.
But relying on this level alone is incredibly dangerous, right?
Oh, yeah. It is the lowest level of control, because it only provides an approximate location of known assets.
And I feel like the most terrifying word in that sentence is known.
Yes, definitely.
Because historical maps are notoriously terrible. I mean, you might be looking at a schematic hand-drawn in the 1980s.
Or even older, yeah.
Right, and it doesn't account for undocumented private utilities, abandoned pipes, or even just the fact that the Earth shifts over time. So if a map can't save you, you are legally mandated to escalate the investigation. You cannot dig based on QLD.
No, absolutely not.
That brings us to quality level C, which the sources describe as essentially searching for clues in the real world.
Yeah, so you take that QLD map, you walk out onto the physical site, and you start cross-referencing the paperwork with reality. QLC is all about surface features.
Like what kind of features?
Well, an operator is looking for, say, utility meters bolted to the side of a building, or pit lids in the sidewalk, or telecom cables running down a wooden pole and just disappearing into the dirt.
Okay, that makes sense.
But the BYDA guidelines also emphasize looking for much subtler environmental clues.
Like covered-up trench lines or weird inconsistencies in the ground itself.
That's a massive one. If an operator spots like a linear depression in the soil or a long patch of asphalt that looks just slightly newer than the rest of the road, that is a huge red flag indicating an asset was buried there, regardless of what the map says.
I have to push back a little on the reliance on QLC, though.
Okay, how come?
Because Honestly, banking your project's safety on ground inconsistencies or following a cable down a pole feels like a massive guessing game. I mean, it's like trying to find buried treasure by looking for a slightly depressed patch of grass.
Right, yeah.
It's an educated guess, but I certainly wouldn't want to bet my life or my company's liability on, a puddle in the asphalt.
Well, the standard actually agrees with your skepticism there. QLC is purely circumstantial evidence. You are still only assuming the underground asset's actual location.
It's just an assumption.
Exactly. And that lack of certainty is exactly what pushes contractors to escalate to quality level B. QLB is where we stop guessing based on surface clues and start actively measuring the subsurface.
So bringing in the heavy tech.
Yes. This requires bringing in a certified locator, a professional armed with precision electromagnetic equipment.
They are essentially running an X-ray over the site.
Conceptually, yeah, that's what it is. The locator is tasked with providing a 3D representation of where these assets actually are. They confirm the approximate alignment, map out where the pipe or cable changes direction, and critically, they measure the asset's depth.
And I imagine during this phase, a smart site manager will direct the locator's attention right to those weird ground inconsistencies they found during QLC.
Oh, 100%. You scan those areas specifically to see if there's an undocumented pipe lurking there.
But even with a professional sweeping the dirt with high-end gear, we still aren't at absolute certainty.
No, we aren't.
Because the guidelines dictate that locators at QLB work to a horizontal tolerance of 300 millimeters, so about a foot, and a vertical tolerance of 500 millimeters, which is over a foot and a half.
Which is pretty significant.
It's a massive margin of error when you consider the sheer destructive force of a civil excavator. And it's especially dangerous because of shared trenches, where multiple different utilities are crammed into the exact same hole.
Yeah, which means QLB is still not enough if you are operating directly inside the danger zone. To legally and safely put heavy machinery near the utilities, you must hit the gold standard, which is quality level A.
QLA.
Right. QLA is the only level where the asset location is considered fully validated. And you don't achieve that with maps or radio signals. You achieve it by putting your actual eyes on the physical pipe.
You have to physically uncover it.
Exactly.
And the industry uses a process called potholing for this, but obviously you can't just hack away at the ground with a steel bucket to find a fragile fiber optic line.
No, that defeats the purpose.
Right. So you have to use NDD, non-destructive digging. This usually involves high-pressure water or air vacuum systems to safely wash the soil away without scratching the utility.
The guidelines do make a practical concession here, though.
Oh, really?
Yeah. If the locator at QLB found the asset to be buried exceptionally deep, using an excavator to remove the top layers of soil is permitted.
Okay.
But the operator must use a spade bucket. That's one with a flat edge and no teeth. And they must immediately switch back to non-destructive methods the moment they approach the asset zone of influence.
That concept of the zone of influence is fascinating to me. It proves that the danger isn't just about the excavator bucket physically striking the pipe. You have to account for the weight and vibration of the machine itself.
Ground movement is highly destructive. I mean, an excavator operating several feet away from a trench can cause the surrounding soil to shift, vibrate, or even collapse.
Wow.
Yeah, that sheer force can snap a brittle old water main or shear a high-capacity fiber optic cable without the machine ever coming into direct contact with the asset.
Just from the weight.
Just from the weight and the vibration.
Mm-hmm.
So the workflow demands that you use QLD and C for the wider area, but inside that critical zone of influence, you must reach QLA and physically validate every single line.
So if we look at the whole process, the linchpin of the entire system is QLB. You need that certified locator with an advanced device to tell you exactly where to perform your QLA potholing.
Exactly.
But there is a massive modern friction point with this system. Traditional locators rely on electromagnetic signals. They induce a current into a metal pipe, read the resulting magnetic field from the surface, and trace the line. But what happens when the infrastructure isn't made of metal?
Well, then you are left with a blind spot the size of a city block.
Here's where it gets really interesting. Modern infrastructure in Australia, and frankly globally, is moving away from metal. We are dealing with polyethylene, or PE, plastic for water and gas pipes.
Yep, plastic everywhere.
And critically, we have things like Australia's NBN, the National Broadband Network, which is this massive telecommunications backbone utilizing glass fiber optic threads encased in plastic conduits.
Right.
You cannot magnetize a plastic water main. You cannot induce an electrical current into a glass fiber optic cable. So to a standard electromagnetic locator, these highly sensitive assets simply do not exist. So how do you trace a pipe that gives off absolutely no signal?
What's fascinating here is the incredibly ingenious physics behind the industry solution, and that is RF markers, or radio frequency markers.
Okay, tell me about these.
These are brilliant, entirely passive devices. They have no internal power source, no batteries to degrade over time, and they require zero maintenance. They are buried directly alongside or just above these non-conductive utilities during the initial installation.
But wait, if they are passive and have no power, how does the surface operator detect them?
They operate on the principle of reflection and resonance, much like a tuning fork.
Oh, interesting.
Yeah, so when a locator on the surface sends a specific radio frequency down into the earth, the internal antenna inside the buried RF marker catches that energy, resonates, and reflects that specific signal back up to the surface. It is essentially an underground sonar system tailored specifically for plastic and glass infrastructure.
That is such a clever workaround. And looking at the TMG article, these markers aren't a one-size-fits-all solution either.
No, not at all.
They come in different form factors depending on the depth of the invisible asset. You have standard marker balls for general utilities and marking joints. You have near-surface markers for shallow fiber drops to residential homes. And then you have large, mid-range, and full-range markers designed for the massive, deep civil infrastructure.
And the engineering goes a step further with strict standardization. These markers are color-coded and frequency-specific, adhering to international and Australian guidelines.
So they speak different languages, basically.
Exactly. A marker buried next to a water pipe is physically tuned to resonate at a completely different frequency than a marker protecting a high-pressure gas line or an NBN telecom cable.
Okay, I see.
So the operator on the surface isn't just getting a generic beep indicating that something is down there. The specific frequency return tells them exactly what is down there.
Okay, so the industry figured out how to tag the invisible assets. But now we hit a serious workflow bottleneck. Time is money on a construction site, and project managers hate downtime.
Right, time is everything.
An operator cannot walk a systematic grid over a massive hyperscale data center facility twice. Like once with an electromagnetic locator sweeping for old metal pipes, and then a second time with a completely different device searching for RF markers. They need to see the entire underground board at once.
Which brings us directly to the engineering of the radio detection MRX locator series. This is where the technology stops being just a tool and becomes a comprehensive solution.
Because it combines them.
Yes. The MRX series are professional-grade units that combine traditional electromagnetic tracing with an integrated RF marker ball antenna into one single device.
So the operator selects simultaneous mode, and as they walk their grid pattern over the target area, the MRX is reading both the magnetic fields from the conductive metal pipes and the reflected radio frequencies from the buried markers at the exact same time.
Exactly. They map the entire hybrid network in a single sweep.
And when the device hits a signal, it provides clear audio and visual alerts, allowing the user to seamlessly switch into peak or null modes. These modes use different antenna configurations to help the operator pinpoint the exact dead center of the asset and calculate its precise depth.
Right, narrows it down.
I was looking at the technical specifications for the MRX, and it highlights a few features that I really want to break down with you, starting with something called power filters. Because if you think about it, the ground beneath a major city isn't quiet.
Oh, it's incredibly noisy.
Right. It is absolutely humming with electricity from dozens of parallel cables. How does a locator filter out the power of a specific target when the whole trench is just a wash of electromagnetic noise?
It is a critical problem. When you have multiple power cables running parallel in a shared trench, the magnetic fields blend together into a broad, confusing wash of noise. It makes isolating one specific line nearly impossible.
So what do power filters do?
The power filters feature solves this by analyzing the harmonic properties of the power signals.
Okay, let's unpack the mechanics of that. What exactly is harmonic in this context?
Good question. When alternating current flows through a power line, say at a standard 50 or 60 hertz, it doesn't just produce that one fundamental frequency. The power ripples out in multiples, or harmonics, like 100 hertz, 150 hertz, and so on.
Okay, I follow.
The MRX uses advanced processing to look at the specific mathematical shape and amplitude of those harmonic ripples. By analyzing that harmonic signature, the device can determine if the signal it's reading is coming from one single distinct power source, or if it is the messy, blended noise of multiple cables grouped together.
That is wild. It's like standing in a room with a choir and using an algorithm to tune out everyone except the baritone.
That's a perfect analogy.
It separates the true signal from the background static at a mathematical level. And there's another feature mentioned that sounds like pure science fiction, fault find.
Oh yeah, fault find is incredible.
The specs say that if you combine the MRX with an A-frame accessory, the locator can pinpoint an insulation sheath fault, like a tiny tear in a cable's protective plastic coating, to within 4 inches or 10 centimeters.
Yeah, 10 centimeters?
How does sticking a giant metal compass into the grass detect a tiny scratch on a buried cable?
It comes down to detecting voltage gradients in the soil. When an operator is trying to find a fault, they use a transmitter to push a specific high-voltage signal into the target cable.
Okay.
Normally, the plastic sheath keeps that signal contained. But where there is a tear or a scratch in the coating, the electrical current physically leaks out of the cable and into the surrounding dirt.
So it essentially creates an electrical bullseye in the ground around the tear.
Precisely. That leaking current creates a voltage gradient. The voltage is highest right at the tear and drops off as it moves through the soil.
And the A-frame finds this.
Yeah, the A-frame accessory has 2 metal spikes. When you stick it into the ground, it measures the tiny difference in voltage between those 2 spikes. The MRX receiver then reads that difference and gives the operator a directional arrow pointing straight toward the center of the bullseye.
That's amazing.
You literally follow the arrows until the voltage difference between the spikes is 0, meaning you are standing directly over the leak. You are finding a microscopic fault from above ground without turning a single shovel of dirt.
That is staggering precision. And having that level of tech is great. But there's a logistical feature called ILOC that really stands out to me.
Oh, the Bluetooth feature.
Right. Because utility locating requires 2 pieces of gear. The receiver you walk around with and the transmitter box you plug into an access point down the street to push the signal into the pipe.
Right, they work together.
On a massive civil site, if the signal gets weak and you need to boost the power, the operator usually has to stop what they are doing and walk a quarter-mile back to the transmitter box.
Which is a huge time sink.
The ILOC feature is essentially a long-range Bluetooth connection that lets the operator control the transmitter's frequency and power output from up to 1,400 feet or 450 meters away. It is a massive workflow fix that keeps the operator actively locating instead of hiking back and forth all day.
Time on site is everything, and reducing operator fatigue directly reduces the chance for human error.
Which brings us to the elephant in the room. We have this incredibly precise tech that filters harmonic noise, reads passive radio markers, and detects microscopic cable tears using voltage gradients in the dirt. It sounds foolproof.
It does, but this raises an important question.
Right.
If we have all of this incredible technology, why do utility strikes still happen? Why are excavators still hitting gas mains?
It's a great question.
The reality is that physics can be unpredictable, and human error is always a factor. The sources detail some very common, incredibly dangerous phenomena that operators face, even when holding the best gear in the world.
So what's the most common trap they fall into?
The first major issue is signal bleed. Electromagnetic signals always want to find the path of least resistance.
It's like water overflowing from one trench into another.
That is a perfect analogy. Imagine you are pumping a location signal into a standard water pipe. If that water pipe physically crosses over or runs very close to a highly conductive high-voltage power line, the signal can literally spill over or bleed from your target utility onto the completely different nearby line. Yeah, and if the operator isn't paying strict attention to the depth readings and signal strength characteristics, they will seamlessly veer off and start tracing the power line instead of the water main.
And if they mark that power line as a water main, the excavator operator thinks they are digging around a safe pipe, hits it, and causes a lethal explosion.
Exactly. That bleed leads directly to what the industry calls ghost signals, where the operator ends up following a parallel phantom line in a congested area. The locator is reading a strong magnetic field, but it's the wrong field.
I noticed the TMG article specifically points out that avoiding these ghost signals is exactly why the higher-end MRX models the MRXG and the SG feature current direction, or CD arrows on the display.
Yes, the CD arrows.
It's not just showing you that a signal is there, it's measuring the specific harmonic direction of the current flowing from your transmitter. It gives the operator visual confirmation that they are still locked onto the actual target and haven't jumped onto a ghost.
The equipment is actively trying to help the human verify their own work. But another major human error point is marker negligence.
What's that?
Often, plastic utilities are buried with a metallic tracer wire running alongside them so they can be found with standard gear. An operator will find that metal wire, trace the line, and lazily assume their job is done, completely ignoring the RF marker detection mode.
Because they think they found the asset.
Right. But utility companies bury specific RF marker balls to indicate critical structural anomalies, like severe bends in the pipe, sudden depth changes, or dead ends. If the operator ignores the markers because they found the tracer wire, they miss the most critical information about the network's physical layout.
So, to combat all of this human error, and to fully comply with modern industry expectations, it is no longer enough to just spray paint a line on the grass and walk away. You have to permanently digitize the record.
And this is where we see the influence of organizations like AUSMA, the Australian Underground Utility Subsurface Mapping Association.
Quite a mouthful.
It is. But they are pushing the industry towards strict, standardized digital mapping. It isn't just about finding the pipe for today's dig, it's about logging its exact coordinates, so the next contractor doesn't have to start from scratch.
And that digital mapping requirement explains the 3 different tiers of the radio detection MRX range.
Exactly.
You have the base MRX, built on their rugged platform, for everyday utility and marker locates. Then you step up to the MRXG, which integrates GNSS, or Global Navigation Satellite System technology, for high-accuracy GPS logging of every point the operator finds. But the absolute top tier is the MRX-SG.
Right. The SG stands for survey grade. The MRX-SG features survey grade GNSS with a staggering 1 to 2 centimeter accuracy.
It's incredibly precise.
It is.
Yeah.
And if we connect this to the bigger economic picture of a construction site, historically, mapping utility required 2 separate processes. You would pay a highly skilled locator to find the pipe and mark the ground, and then you would pay a separate, highly compensated surveyor to walk behind them with a dedicated GPS pole to record the coordinates to the civil engineers.
2 technicians, 2 salaries, twice the time on site.
The MRX-SG combines advanced utility locating, RF marker detection, and centimeter-accurate survey mapping into one single tool operated by one person.
Wow.
The data they collect can be instantly exported and integrated directly into GIS geographic information systems, which are the digital map layers cities use to manage their infrastructure, or into BIM workflows, which are the 3D digital twin models used by architects and engineers.
So it entirely eliminates the need for a separate survey team, which drastically reduces the total project costs while actually improving the integrity of the data because there's no miscommunication between the locator and the surveyor.
That's a huge step forward for the industry.
So what does this all mean? For you listening, it means the next time you are walking your dog and you see those bright pink, yellow, and blue spray-painted lines crisscrossing the sidewalk, or you walk past a civil construction site with dirt piled up everywhere, you will know that you aren't just looking at random graffiti or a simple hole in the ground.
Definitely not.
You are looking at the result of a highly regulated, technologically advanced operation. Achieving that AS5488 quality level A isn't just about digging a hole. It is an intricate dance of analyzing harmonic power filters, tuning into precise RF marker frequencies, measuring voltage gradients in the dirt, and utilizing centimeter-accurate satellite mapping, all working together to keep the invisible modern world running safely.
It truly is a hidden ballet of physics, technology, and extreme caution. But as we wrap up this deep dive, I want to leave you with a final thought to ponder, drawn directly from a detail in the BYDA guidelines regarding those shared trenches.
Okay, let's hear it.
To save space and excavation costs in our increasingly crowded cities, utility companies are increasingly cramming multiple distinct assets, high-voltage power, delicate NBN fiber optics, and pressurized gas into the exact same narrow trench.
Which sounds like a recipe for trouble.
Well, we talked about the dangers of signal bleed and ghost signals today. If the underground is already this crowded and noisy, how much more chaotic will it become 10 or 20 years from now? As our subterranean world gets denser and denser, will we eventually hit a physical limit with our current electromagnetic technology, forcing us to invent a completely new way to separate the signals from the noise?